the Medical AI Podcast.
Hello and welcome to the Medical AI Podcast, a 30-minute thrill ride of big ideas. We are Dr. Felix Beecher and Joe McKeating, and we talk to a range of top guests from scientists to industry innovators to philosophers.
Welcome to the Medical AI Podcast, where we explore the nexus of healthcare and artificial intelligence. I'm your host, Joe McKeating. Today, I have the privilege of speaking with Dr. Dan Heller, a pioneering biomedical engineer who is helping advance cancer detection. Dr. Heller leads the Cancer Nanomedicine Laboratory at Memorial Sloan Kettering Cancer Center in New York City, where he and his team develop advanced diagnostic technologies. His lab recently made headlines for creating a nanosensor nose that can sniff out ovarian cancer. Using carbon nanotubes and machine learning, this artificial olfaction technology was able to identify ovarian cancer, making treatment more feasible. In addition to his groundbreaking work in the lab, Dr. Heller co-directs the Pat and Ian Cook Doctoral Program in Cancer Engineering at Memorial Sloan Kettering, is a member of the Molecular Pharmacology Program at the Sloan Kettering Institute, and serves as a professor at the Weill Cornell Graduate School of Medical Sciences. Dr. Heller, thank you for joining me on the Medical AI Podcast.
Great to be here, Joe.
So, to begin, I think leading a groundbreaking, cutting-edge bioengineering medical laboratory at one of the most esteemed cancer institutes in the world, people may be surprised to hear about your path to get there and your original academic background, which also led you to teach as a middle school science teacher for a bit. Could you talk a bit about your journey and how you got here and what you learned in those different roles?
Absolutely. It certainly wasn't direct. I was actually a history major in college, and but really got interested in education, and I started doing chemistry demonstrations at the local science museum in Houston, where I was in college, and I ended up deciding to go be a teacher. And applied to be either a history teacher or a science teacher. I ended up getting the science teacher job and ended up loving it. And so I was a full-time middle school science teacher for 2 years. And I don't know if that I really imparted tons of amazing wisdom to the kids, but I know that they really affected me. And when I was teaching the middle school science fair competition, or kind of teaching kids to do experiments, I realized, this must be what it's like to be a professor running a research lab, except I had a bunch of 8th graders, but actually they did really great, and mentoring students to do science was really where I kind of found my calling, that's how I found my calling in mentoring these middle school students, and it got me really excited about doing science and mentoring people to do science, and that's how I decided to go be a scientist full time and be a professor.
And what was that process like when you decided to go from teaching middle school science? How did you then go from there to leading the Nanomedicine Cancer Laboratory?
Yeah, that it was also not, you can kind of connect the dots looking backward, but never looking forward. Well, when I was, while I was in that second year of teaching, I started taking organic chemistry at night school. And while doing that, I realized, okay, chemistry is it. I can do this. And kind of to prove to myself. And then after teaching for 2 years, I stopped and I started taking additional classes, get the math that I needed, and physical chemistry. and started asking around if I can do volunteering in laboratories, and started volunteering in a materials chemistry lab that was actually collaborating with a circadian neurobiology lab. At the same time, I was also working with one of a carbon or a physical chemist, actually one of the people who helped discover the buckyball, the C60 dome or nanoparticle, which kind of ushered in the nanotechnology revolution. And so I was doing this kind of simultaneous research in these different labs, and that all got me interested in both nanotechnology and biomedical research.
And what, in a nutshell, we're going to get into some of the specifics and some of the projects that you're working on, but generally, what does the Cancer Nanomedicine Laboratory do?
So our lab is a biomedical engineering lab in a cancer center. So we're really interested in building technologies. And I like to tell people, well, the difference between our lab and a biology lab is that we first think about, what technologies that we could build to solve problems. And some of those problems might be, we want to make a technology that improves the ability to detect something, to do basic science biology research. But we have the goal of building new technologies to address problems. And then and in a place like this, a cancer center with a lot of biology labs and clinical laboratories and clinicians around us, we're kind of surrounded by problems, and which is amazing to be an engineer with the goal of building new technologies, surrounded by problems and questions problems to solve and questions to answer. And so that's why I feel like we're kids in a candy store in this kind of environment. And I always think that biomedical engineering or engineers should be in medical centers doing biomedical research, because there's just so many, because they're right where the problems are. And so that's what we do. And we are focused specifically on the development of nanotechnologies, nanomedicines, drug delivery, nanoparticles, as well as sensors, nanosensors for detection.
When you say you're right there where all the problems are going on, it made me think. I think listeners may be interested to know, what is that process like for determining what you want to develop technologies for? Is it in consult with physicians? Are there brainstorms at your lab? Are you in a conference room? People propose things and you narrow it down. How do you make those decisions?
When we meet people here, we ask, what problems are you working on, or they tell us what problems they're working on. We might see them give a talk, but actually, the way I got into ovarian cancer research was that I was in the lobby of the building where my lab is, where I am right now, and I started talking to a gynecologic oncologist, someone who does who does clinical work or treats patients with ovarian cancer and other gynecologic cancers. And he said, what do you do? And I said, well, we make sensors, nanosensors. And he said, well, we really need a sensor because we need to detect ovarian cancer. And it really, he taught me all about how there's such a big need in the detection of ovarian cancer and early detection. And really, that's how it started, right in the lobby of this building. The clinician, he was actually a clinical scientist, had a lab, and we started working together. And that really made us focused on ovarian cancer detection for the last 10 years.
Yeah, I'd like to get back to the ovarian cancer and how you're using machine learning. But before that, I think just even to give listeners a sense of the array of problems that you're working on, you gave a lecture recently about using nanoparticles for medulloblastoma, if I'm saying that correctly, which is, as I understand, is the most common form of brain cancer in children. And a problem there is with what you call the blood-brain barrier and targeting a protein named called P-selectin. And I think even just to give a quick overview of that might be really interesting to listeners and give them a sense of how many different things you're working on there.
Absolutely. So that's on the drug delivery side of my lab, and I guess we kind of think about our lab as kind of having two areas: the sensors and drug delivery. And the drug delivery area is where we think about how to get drugs to the sites of disease more effectively, so we treat the disease better, and how can we prevent the side effects that's caused by really any drug. And so if we can get drugs specifically to the site of cancer, and that's the area of targeted drug delivery, that would really improve treatments. And when you take a drug or someone gets infused with a chemotherapy, it goes everywhere. And even in the area or the time of precision medicine and targeted therapeutics, that precision and that targeting usually means that the drug only affects the tissue or the protein that is in that tumor. And in reality, yes, there is this idea that a molecule could only affect that the target, the molecule that is involved in the cancer that we want it to. But more often than not, and really almost all the time, that drug has some sort of side effects because it might stick to something that we don't want it to, or stick to the right target, but that target, that protein, is also involved in other processes in the body that we need. So we really need to think about that type of precision and targeting, as well as targeted drug delivery, where we could think about getting the drug to go more specifically where we want it, and sometimes even more importantly, to avoid its exposure to tissues in the body where that drug might cause problems, side effects. And so when we think about targeting the blood-brain barrier or brain cancers, we think about the blood-brain barrier, which is this barrier where many drugs really just can't effectively get into the brain, can't get to a disease site in the brain. And this is a problem in brain cancers, but also many other diseases that are involved in the brain, certainly Alzheimer's and other neurodegenerative diseases and psychiatric diseases. And so getting a drug there is often a big hurdle. And so someone that's made a drug that they think was going to really work, and it might work in a cell, then they realize that it can't get to the brain unless you maybe increase the dose 10 times more than you want to. And so we've been focusing on brain tumors. And we really got interested in it when some member of my lab was giving a talk, kind of similar story to the ovarian cancer guy. And this pediatric neurologist was in the back of the room and said, "Oh, can you get your particles across the blood-brain barrier?" And we never tried that. But we knew it was hard. So I said, "Well, probably not, but we could try it." And this pediatric neurologist was also a mouse geneticist who had models of this pediatric brain tumor called medulloblastoma. And and the interesting thing about this model was that it modeled the intact blood-brain barrier. So we knew that if we could get our particles to the tumor in this model, then maybe we could get it to really across a human blood-brain barrier. And so we started doing the work, and it turns out that our particle was getting to tumors because we had already been working on this area called this protein called p-selectin, which shows up on the blood vessel in a wound site or in a site of inflammation. And our particle sticks to it and can get across the blood vessel in that site of inflammation. And it turns out that a tumor is like a wound that never heals. So p-selectin is already turned on in many tumors, and our particle can stick to it in this and get across the blood vessel. And what we did with our colleague, his name is Praveen Raju, he's now at Mount Sinai School of Medicine. We started working very carefully with him to determine whether we can get across this blood-brain barrier in this tumor, and then treat the tumor. And it turned out that we can put many types of drugs inside of this particle and get it across this intact blood-brain barrier in this brain tumor model, and effectively treat it and prevent side effects like a drug that physicians were really interested in using to treat this disease. Was a drug that inhibits the sonic hedgehog pathway, which actually drives many medulloblastoma cancers. And people might recognize Sonic Hedgehog from the video game, but this particular gene which was named Sonic because of its importance, is important in the driving of this tumor. But the problem was that the the drug can also cause growth defects. Basically, can fuse growth plates in children, so it couldn't really be used in children. And we found, at least in this tumor model, that we can prevent the drug. We could give the drug at a much lower dose, prevent it from causing these growth defects, but can effectively treat the tumor.
And do you think is there any machine learning aspect to that? I know we're going to get into some of the more specific machine learning in your lab, but even with this specifically, when listeners are hearing this, and when we talk about machine learning and deep learning and artificial intelligence in medicine, as we get further along, maybe using some of those models for not just drug discovery, but also maybe simulating how they'll work. Do you think this helps move us in a direction where chemotherapy might be a thing of the past, or how do you see that issue?
Yeah, so we've been using AI in our nanoparticle drug development area, really to optimize the design of nanoparticles. So we've found that our drugs we can make nanoparticles out of many types of drugs, but that can target p-selectin. But we wanted to, if we did that empirically, just try everything out in the lab, it would take a really long time. So we realized that if we could use the drug structure, the molecular structure of a drug, and use that to predict whether it can form a nanoparticle, that would be really exciting, just on the ability to do this kind of nanoparticle development. And because we found that many people at Sloan Kettering and many other institutions are making new drugs, and but they're not, they aren't targeted enough, or have different issues, toxicity, or just ability to get to the tumor. And so if we could make many drugs fit into these nanoparticles, that would be exciting. And so what we used was AI, and we first used just computational chemistry, so kind of a little even simpler than AI methods to find correlations between the drug structure and whether they could package into a nanoparticle. But then we know that using more and more powerful tools, including more machine learning type tools, we can improve this this ability, and then try to predict things like more than just whether a drug can form a nanoparticle, but whether a nanoparticle with a given composition could get across a barrier or into the place we want it to be, or be effective. And so we've started slow with just kind of figuring out whether we can package the particles, but package a drug into a particle. But now we really are excited about moving this ahead. And I have a colleague who actually was worked in my lab and was trained on this. And his background was actually electronic music, and got into this area of computational chemistry and drug discovery. And now he's started his own lab where he's really focused even more than we are on using AI in nanoparticle development.
I think when we think of artificial intelligence in general, not just in medicine, some of the biggest breakthroughs, or at least demonstrations, were shown in gaming. So if you remember when AlphaGo played, one of the top Go players in the world, and
Right.
One of the interesting things in that, I think it was a 5-series match, but maybe in the third or fourth game, the artificial intelligence made a move that seemed very counterintuitive to everyone watching, and they thought, oh, it just messed up. And it turned out to be this novel, actually brilliant move. Are we at a point yet when you're designing these nanoparticles, say, where you're seeing artificial intelligence do things in ways where you look at it and you go, oh my goodness, we wouldn't have thought of doing it that way? Or is it still mostly human input and it's increasing your efficiency? Or is it really starting to go outside those lines where it's thinking the way a human might not be able to think?
Oh, absolutely. There's ways that where computational tools maybe even kind of more simpler than then what we would call AI or simpler than machine learning have really gotten us to places where we couldn't get. And I think this is true in the computational drug discovery field. And there are companies out there that have already started and have been developing drugs that nobody would have thought about developing a certain molecule the way they had, unless they had the computational tools. So certainly on just developing those drugs in small molecules, that's true for making drugs, but also on our drug discovery, our drug development, nano drug development areas. We found insights using computational tools like quantitative structure activity relationship based tools, so QSAR they call it, where that have just made allowed us to get insights that we would have never come up with without it. For instance, QSAR is an area where you could really make a number, a score out of a molecule. So you can take a molecule, a small molecule drug, and you can compute the molecular weight. That's easy or simple. And you can also count the number of hydrogen bonding donors and acceptors, and that's another number that you can get. But then you can get all sorts of more complex measurements, like nearest neighbor calculations of carbons to other part of, or oxygens to other part of the molecule, a kind of a molecular map. Or you can make measurements of, or you can compute, say, how electrostatic different parts or how electronegative different parts of the molecule are. And so there's many numbers, thousands of numbers that you can make get from a molecule, just the structure that you can draw on a piece of paper or on a screen. And then from that, you can make lots of inferences, and you can start to use these computational tools and machine learning tools that can make correlations and inferences that nobody would be able to make. And we started doing that even in 2018. We published our first paper on this using these QSAR tools, and we found insights about how to make a drug fit a nanoparticle, which we would never have made without these computational methods.
That brings me to one last question on this topic. With the artificial intelligence, is it as if it's throwing a million things at the wall and seeing what sticks, or is it making these computations with a high degree of accuracy and credibility?
We would start with a training set. So we've started even without a kind of a sophisticated AI algorithm, but with this QSAR type software, which exists and is available for especially in academic research. And companies can license this. We can make a training set of, say, molecules that fit our nanoparticle, can form a nanoparticle, and molecules that can't. And that's kind of how we started with our work. We actually were just kind of seeing this random pattern of, we couldn't figure out why one molecule would make a nanoparticle with our method and others wouldn't. So we made a training set and fed it into this simple QSAR software, which had thousands of different calculations in it, but really just was doing a correlation of its different scores of these different types of calculations, like electronegativity and such, with our training set of a vector of data saying whether a given drug structure formed or didn't form. And with that, we already had found something that, in this case, we were very lucky and got this super high score with a few different descriptors. And we realized we were descriptors, meaning these molecular descriptors. And we realized we were onto something. So really just a very simple, or kind of a simple tool, especially with now, compared to the type of algorithms we have now, a few years ago, got us into this. And so even with a quite small training set, I think our original training set was only 16 molecules, already got us to a really high correlation of certain descriptors of molecules that predicted the formation of our particles.
And I want to get back to the ovarian cancer and how you're using machine learning there. But before we do, I'll just quickly say I know that I'm interested, as is my co-host, Dr. Felix Beecher, who I do the podcast with, in what we call real-world AI. And so oftentimes when people are thinking about artificial intelligence, especially in the general public, kind of because of the media portrayal of it, you go, well, it could write you a college essay, but not sure exactly what you'd use it for beyond that. Now Tesla had the full self-driving, great example of real world artificial intelligence. When I came across your research using carbon nanotubes, which you'll explain better than I am, but than I can, but they're, maybe a human hair would be 10,000 times wider or 100,000 times wider, and how maybe it's volatile organic compounds are interacting with those. And I thought this is really interesting because it is mixing the physical world, the world of biology, with software, and a great example of real world AI. And so getting back to the ovarian cancer, how are you using machine learning there? And these carbon nanotubes also sound, whether or not they're artificial intelligence related per se, or seem pretty technologically advanced way to do things.
Yeah, so carbon nanotubes are kind of my first love in nanoscience. I did my PhD work in them, and when I was first starting out in my PhD work, it was recently discovered that they glow. These carbon nanotubes are just rods made of graphitic carbon, meaning everything's a hexagonal shape of carbons, 6 carbons, and in a hexagon, and then it kind of becomes this mesh, and that's that's what graphene is, or graphite is. It's just this kind of these flakes of sheets of graphite. But if you roll them into a tube, and that tube is really small, like a nanometer in diameter, which is 100,000 times smaller than the diameter of the hair of a human hair, you get this interesting, these really different properties than what you get from normal graphite or a single sheet of it, graphene even. And these tubes, depending on exactly how the carbons line up when it's rolled into this tube, they glow. They're fluorescent. And they're fluorescent, and those are actually, those materials are now semiconducting. And actually, from the time of this podcast, just last week, there was a Nobel Prize in an area of nanotechnology, actually 2 areas, but one of them was quantum dots. And quantum dots are these spheres that are semiconducting crystals, and they glow because they trap electrons into a very small space, and allow basically the electrons to then recombine with areas of positive charge called holes, and then and that causes emission, fluorescence. And a carbon nanotube can also do that. It can trap electrons close enough, kind of confine electrons in a small enough space, because these tubes of carbon are 1 nanometer in diameter. And so with these glowing tubes, it turns out that they can be really good sensors as well. They don't just glow, but their emission, their fluorescence, the light that comes from them, when you have to shoot them with light, but when they glow, the light that comes from them can be very sensitive to their environment. And the reason that these can be good sensors, and maybe probably better sensors than quantum dots, is that the carbon nanotube fluorescence comes from these carbons, and the carbons are all on the surface because there's nothing in a carbon nanotube in the middle. It's a hollow tube, and so you've got this hollow tube of carbon, and the carbon is causing it to glow. The electrons that are attached to those carbons are causing it to glow, and something that gets near it can perturb that fluorescence and change both the intensity and the wavelength, the color of that fluorescence. And so you get this really interesting material, which is basically intrinsically, at its nature, a sensor, something that can respond. The light can respond to things near its surface. And what we do in our lab is try to harness that fluorescence and that ability to detect anything, or anything that's near its surface, to make it more specific. And so for a while now, the last many years, people have been making sensors, trying to make the sensing specific to certain molecules, like to put an antibody on an nanotube surface, and you can detect something like an antigen, a biomarker in disease, and we've done that. And but we realized that, well, if they can really be used to detect anything, let's see if we can make a sensor that we can basically create enough diversity into many carbon nanotube sensors, put them into a complex fluid like like blood, and then based on the things that stick to that from the blood that stick to the carbon nanotubes, can we get some like a fingerprint of the disease, where things that stick to the in disease in blood that comes from a patient with cancer might look different than the things that stick to it in a healthy patient. And if those things are different that's sticking to it, maybe the fluorescence will change with a different pattern. And that if there's a different pattern of changes of fluorescence of these nanotubes in that when these nanotubes were introduced to cancer patient blood from healthy person blood, then we can maybe get a pattern that can be recognized by AI, and then we can use that pattern to then harness, so that when the next person comes and we basically and we use their blood and put their blood into the sensor array, then we could detect cancer, and we could make a diagnostic where we didn't know exactly what the biomarker was that we were going to detect, but we knew that something different is binding, and that the sensor array combined with machine learning can recognize cancer patient compared to healthy blood. And there's an analogy for this. There's several analogies, but the idea is that this is a detection method that's using perception. So it's so that your nose has only a few hundred olfactory receptors, but you can differentiate something like 1 trillion different smells. And so using the pattern of what odor molecules bind to what olfactory receptors, and your brain doing pattern matching out of all those binding affinities and differences, you can now identify a smell out of 1 trillion different possible smells. And so the same goes here. And people have been using this same kind of method for making what they call the electronic nose, and using olfaction and looking at volatile organic compounds, say in the breath. But we did this as apply it to serum, to blood.
And even for the sake of listeners and myself visualizing this, what this looks like, what this process looks like, when you're talking about taking a bundle, if that's the correct term, of these nanotubes and putting them into the blood, whether it's the cancerous blood or the healthy blood, what does it look like? If we were there in your lab, would we be even able to see this bundle of carbon nanotubes? Are you putting them in with a little tweezer? Is the bundle so big that it's a pretty visually obvious? We'll start with that.
So the nice thing about this is that we can deal with these carbon nanotubes, which are we buy as a powder. So you can purchase these things. It looks like soot, a black powder, and what we do is we wrap these nanotubes in different polymers and even single-stranded DNA that sticks really well to the nanotubes. And different kinds of polymers can be used to solubilize these, suspend these in solution. We do this because it's much easier to now work with these, especially if we want to put them in blood. We want these to be in a suspension, something that we can draw up with a pipette and spew out into a little plate. And so we want to see they're now all in liquid form, but if they're concentrated enough, you can still see that they're grayish. Actually, if you separate the different kinds of nanotubes, they become different colors. You can even get nanotubes that look blue and red and purple. But so we have a small amount of these fibers, these tiny little nanotubes, all floating around in a solution. And they're wrapped in these different polymers and wrappings, and that allows us to create diversity in what is sticking to the surface of these nanotubes, because we want an array or a bunch of different nanotubes that all bind to the serum maybe differently. So some of these nanotubes might be sensitive to certain proteins in serum and others are not. And so we have now a kind of a diversity here. And we even add more diversity by chemically modifying these a little bit to now make them sensitive to different chemical groups and different chemical parts of the protein, or parts of different proteins. And so now we have an array of maybe 5 or 10 different nanotube types. and we'll put them in different little cups, different little wells of a well plate. And so now we're integrating these nanotubes into a similar kind of form factor that's used in many people's labs in biomedical research, where we can put them into a well plate of maybe 96, about 100 or several hundred different wells, and a patient's blood will be put into these wells as well. And so if we have 10 different sensors, we'll put the same patient's blood into each of those 10 different little cups of this plate. And now we've made 10 different measurements from one person's blood, where there's an array of data. And now there's data from each nanotube actually can get 4 different types of intensity and wavelength measurements. So we get basically 4 different features from those nanotubes. And so say from 10 different nanotubes, we can get 40 different features, different fluorescent features that we use in our machine learning model.
And you gave the background earlier of how you landed on ovarian cancer from the meeting with one of your colleagues. As I understand, this is a especially vicious form of cancer when not detected. I think we talked something like a 15% 5-year survival rate if it's metastasized. If it's working here with the ovarian cancer, do you see any barrier, if you will, to this being applicable to basically any other kind of cancer, whether it be blood cancers or anything else? If it works here, should it work elsewhere, or is this a pretty specific use case?
Oh, absolutely. So there's no barrier to using this for not only any cancer, but any other indication where you have blood from patients. And so now what's actually binding to this from the blood to the nanotube is different proteins and even small molecules, metabolites, hormones, many different things. We don't know exactly what's binding to create our kind of pattern of responses. But we can take these same nanotubes or different sets of nanotubes. We have kind of many ability to kind of expand the set of nanotubes if we need to, but we can take these nanotubes and we can introduce them to blood of any patients, and all we need really is enough patients from any indication and a control set, a control cohort of patients, and then we can see whether we can detect whether the machine learning algorithm that we train with these sensors can differentiate whatever indication, disease, cancer that we want. And so the hope is we can get like a universal set of sensors where we don't have to change out our different sensors, that we have the same carbon nanotubes that can detect anything. But the nice thing is when you can get blood from different patients, you can ask many, many different questions about many, many different types of diseases, as long as you can have a big enough set of blood to start getting meaningful information. And just like many people know with AI, there's always a data limitation. You need enough data. AI is really data hungry, and so we need, really we want hundreds of patients for any indication to just start to see whether we're really getting a differentiation between the signals that are coming from a cancer patient and a healthy patient or a patient without that cancer, and or with maybe other diseases that we could be conflated with that cancer by many other methods. And so we think that really the sky's the limit in where this can go. And we're already working to see different indications where we can differentiate different kinds of patients from each other, or disease from healthy.
Yeah, any model, right, is only going to be as good as the data it's working with. A question that comes up a lot regarding AI is explainability. And in some context, it wouldn't be quite as important, right? If someone wants to help writing an email, not a big deal. If it's cancer detection, I would think that explainability is needed, is going to be demanded there. Where is that line? How close are we to that? Do we understand what these machine learning models are doing, and could we work backwards on how they came to a conclusion? Where are we on that?
Yeah, that's something I think about all the time, and we definitely don't. We want to make sure that we're not being tricked. There's famous examples of of people kind of looking at pattern matching even before current AI methods, and finding that they can, instead of detecting the cancer, they're detecting where the sample came from, whether it came from one hospital or another, using, say, mass spectrometry methods or types of data, which has been definitely an area where AI has found that there's a good way to get lots of data. But in our with our sensors, we absolutely want to find out what we're detecting and what's the ground truth. And even before thinking about just the AI algorithm, we want to know what's sticking to these sensors. That, if we did find an algorithm that we could a great predictive score with an algorithm, we want to know, well, it's caused by something sticking to these sensors, and so we can use approaches like washing off the sensor or the sensors that enable the detection of the disease, to see what was sticking to them, and can we get a ground truth? Can we see if there's some protein or other molecule there that stuck to these sensors that was causing that sensitivity? Now, most people want to find one biomarker for a disease, and we are a little bit skeptical that we're going to, by washing off these sensors, we're going to find the magic biomarker that stuck to these sensors that gave us that great response from our algorithm. We're probably going to get a lot of different things that stuck to these sensors, some of which turned on, some of which got turned off. We got some got more plentiful, some got less plentiful in disease versus healthy. But we think that there is a way to get to some sort of ground truth with this. It may not get us really satisfying ground truth, but at least there's some way to explain, by washing off what stuck to these, explain what caused the detection of the disease. And so we're actively working in that direction, and working with mass spectrometrists to find those things that would have been sticking to our sensor that enabled the detection of disease. And also trying to make sure that we don't get fooled by these things, and make sure that we're not detecting inadvertently, like the way that these samples were stored, or whether cancer patients we're just taking cancer drugs that showed up that we're binding to our sensor. So we're very cognizant that there's definitely ways to be fooled, and that we can't take any result from this at face value.
Well, Dr. Heller, this has been great. Before we let you go, what at this intersection of nanomedicine and artificial intelligence are you most excited about, either at your lab or in the field in general? And are there any predictions that you'd like to make about where we might be 5-10 years from now?
Oh, wow. A prediction. That's always the difficulty. I really think that using either our approach for, or similar approaches for sensing, or other detection methods and analytes like circulating tumor DNA, microRNA, proteomics, that there's going to be a way to start really getting meaningful detection of disease. We already saw it with certain companies out there that have gotten, definitely more than we've seen already in terms of detection. And so I think by using a combination of markers and new biomarkers and machine learning, that there's going to really be ways to detect disease earlier, detect disease better, get a way to triage disease with a liquid biopsy, just with blood or urine, or saliva or sweat. People are going to get more and more information that's going to be meaningful, and I'm really excited about and this is just on the detection side. I certainly am. I'm also optimistic on the disease treatment side with new types of with computational chemistry and other methods for making drugs. But really on the detection side, I think it's a really good problem that where machine learning and AI methods is going to really make meaningful progress.
Well, Dr. Heller, we wish you and your colleagues at the Cancer Nanomedicine Lab the best. It's been a fascinating discussion. We hope that you'll join us again in the future.
Thanks so much, Joe. Great to be on here.
Thank you for listening. This has been the Medical AI Podcast. We are Felix Beecher and Joe McKeating. Ping us on LinkedIn if you have any ideas on new guests. See you next time.